So having taught differential equations for a while, there's one common thing which really makes students struggle more than anything else. And you might think, it's a topic in differential equations that students have the hardest time with. But actually, it's not anything with differential equations. If we represent all of our challenges that we see students having, there's one thing that dominates. And this dominating thing is algebra. More than anything else, your ability to do algebra will determine how you succeed in the class. And so we're going to take some time to review the basics. Nothing exotic. You don't need to know anything secret or complicated. It's all easy stuff. And once we have our algebra down, then we can just sort of channel our inner Pac-Man and just gobble up the rest of the problems. So let's go and talk about algebra. So the first thing we should talk about are polynomials. Now, these are going to be used over and over and over again. So we want to make sure we're comfortable with polynomials. And there's 3 skills we want to be able to do. Our first is to be able to expand. Now, you might know the acronym FOIL, which stands for first, outer, inner, last. But essentially, what do we do? Well, let's make up an example. It's not hard to make up examples, right? So we'll just say I want x squared plus 3x minus 5, and I want to multiply that by x plus 1. What do we do? What do we do? Now, you might say, wait, FOIL, that doesn't work because there's 3 pieces here. And usually it's 2 pieces times 2 pieces. Well, what does FOIL really say to do? FOIL says, look, every term matches up with every term. So we have 2 pieces, and so what we're going to do is multiply and look at ways to combine, each with each. And so what does that mean? Well, for instance, we're going to take the x squared, multiply by the x, and that's x cubed. X squared multiplies by 1. That's x squared. 3x multiplies by x. That's a 3x squared. 3x multiplies by 1. That's 3x. Minus 5 times x. Minus 5x. And minus 5 times 1. Minus 5. Right? So each term in the first, each term in the second comes together. Now, we'll say this a couple of times, and the reason we say it is because it shows up a lot in mistakes. Keep track of your minus signs. Minus signs are important, and oftentimes when we make mistakes, they're a first place to check. And now we just clean up. The way we clean up is we combine like powers of x. So we have just a single x cubed. We have 2 x squared terms. So there's an x squared and a 3x squared. That makes 4x squared. We have a 3x subtract 5x. That's minus 2x. And then we have a minus 5. And there we go. So that's an example of expanding. Oftentimes it'll just be FOIL when we have like x plus 3 times x minus 4. But, we want to be able to do it in general. And there may be 1 or 2 times when we want to handle something more complicated like this. And one of the things we'll do at the very end is series, and we want to be able to handle multiplying really big things together. And just remember each with each, and then you're like, perfect. I know what to do. I know what to do. All right, what about factoring? How does that work? Well, with factoring, let's say we'll do an example. We have y squared minus 2y minus 15. And maybe we'll set it equal to 0. All right. And we say, well, what's the value of y that makes this work? Now, the goal is to say what? Well, I want to somehow multiply this into 2 terms. And, okay, well, why? Well, we'll get to that in a second. Now, y squared makes it not so bad. You're probably going to have a y and a y. Say, okay, what's two things that multiply to get minus 15, but add to get minus 2? Right? Because this term comes from multiplying the two pieces at the end. This middle term comes from adding the two pieces at the end. Well, minus 15, 15 is 3 times 5. There's not much else you can do. You could do 1 times 15, but no way you're going to get 2 from 1 and 15. All right, so 3 and 5. One of them has to be a negative. One has to be a positive. We need to end up with a minus 2, so the negative should be to the bigger term. So I'm thinking minus 5 and plus 3. Now, you might say, okay, well, maybe, will we ever know? Well, yeah, we can check, right? One of the things we want to get into the habit of is check our work when we can. How do we check? Well, we multiply it, right? Y times y, good, y squared. We have 3y minus 5y, minus 2y, good. Minus 5 times 3, minus 15. Success. Now, why did we do all of this? Well, the reason we did all of this was to say, okay, what values of y makes this true? Now here, it's not so obvious, but here, notice we have two things multiplying, and out comes 0. Well, how could that happen? Well, the only way two things can multiply and the output is 0 is if one of them is 0. So you say, oh, so what we're saying here is that either this y minus 5 is 0, which would say y equals 5, or this y plus 3 equals 0, which says y equals negative 3. All right, great, success, kapla. All right, but what if it was more complicated? More complicated, let's see, do I have an example? Yeah, let's try something trickier. 8z squared plus 2z minus 15 equals 0. Now, does this factor? Maybe, not so clear. So what can you do? Well, don't forget that you always have the quadratic formula as a backup, a safety net, if you will. So you can say, okay, well, z is negative b plus minus the square root b squared, that's 4, minus 4 times ac. So 4 times 8 times 15. Oh, this is going to get interesting. Well, that's actually a negative 15, so that makes that a plus, all over 2a. Okay, Well, what can we do? Well, we can let's hope this works out. And I hope it does. Well, the 4's are common. You can pull that out. And so when you do that, the square root of 4 makes 2, so that's negative 2 plus minus 2, square root of 1 plus 8 times 15. Well, that's 8 times 10 is 80. 8 times 5 is 120. All over 16. Now that makes 121 inside the square root. Oh, well, that's a nice number. So that makes negative 2 plus minus 2 times 11. That's 22 over 16. Or you get negative 2 plus 20. Well, that would be, negative 2 plus 22 would make 20. So you get 20 over 16. And then negative 2 minus 22 is minus 24 over 16. And 20 over 16, well, you can divide out by a factor of 4. That gives us 5/4. 24 over 16, factor of 8, negative 3/2. And so we found our roots. Now we can go back and say, oh, how does that make this factor? Well, it tells us that what we look like is something along the lines of the following. Namely, we look like z minus this root 5 over 4, and z minus this root of minus 3 over 2 is plus 3 over 2. And now you say, well, are these the same? No. What's different? Well, this 8, right? Because here you have z times z makes z squared. We want 8z squared. All right, throw an 8 in. and life is good. You've made it work. So, when in doubt, you always have the quadratic formula to fall back on. All right, great. So we can expand, we can factor, and in worst case, if we need it, we always have the quadratic formula as our safety net. Completing the square. Now sometimes we sort of like, yeah, all right, well, we've got the quadratic formula. Do we really need this technique? And the answer is yes. This will actually be important, especially as we get towards the end of the course. So let's remind ourselves what we mean when we talk about completing the square. Well, the name is, of course, suggestive. We want to make something that's a square. So let's look at what squares look like. You have a plus b squared. That's a squared plus 2ab plus b squared. All right, so that's a clue. In fact, you should kind of have this in your back pocket. You never know when you might want to pull it out and say, aha, when can I use this? You'll use it more than you think. All right, so suppose we have something like a t squared plus 8t plus 20. All right. Now, to say completing the square, it says, I want to make the stuff with the t look like a square. So you say, okay, well, I've got my square here. So you say, all right, that's great. So what does this mean? Well, it says, hey, here's my a squared. So this part here needs to be my 2ab. And you say, okay, well, that's fine. That means that this 8 is what? Well, that's 2b, or not 2b. No, it is 2b, right? Because the a is the t. So you say, okay, well, what I'll do is I'll take that coefficient of the middle term, and I'll divide it by 2, because of that 2. And so this would give us, we'll take t squared plus 8t, take the middle term, divide by 2, and you say, well, that would be 4. So you say, okay, so I need to add 16. So I have my a squared, 2ab, b squared. And I say, well, wait a second, that's 20, not 16. No problem, plus 4, right? So what we've done is we've sort of broken that term on the end into 2 pieces. And one that's helpful for us in getting the right form, and then the rest. And then we'll deal with the rest in whatever way we need to. And now we say, okay, well, all our work is to say, hey, this part looks like t plus 4 squared. And the 4, well, we can write it as 2 squared if we wanted to, or as 4, whatever you like. And there we go, completing the square. No big surprises. Now, one small word of warning. When you're doing completing the square, be careful that you want a 1 in front of this first term. And if it's not a 1, what do? It's not that you give up, because that's not how we roll. That's not our class. You say, well, if it's not a 1, make it a 1. Factor out what you need to make it work. And there we go. Those are our polynomial tools. Not very many, and hopefully you're going to be like, I know all of these things. Great. Well, then you'll be in good shape. Before we leave, let's write down one more thing with polynomials. We wrote down, of course, a plus b squared. I would say that the other thing you should know by heart is a plus b times a minus b. This shows up a lot. And what is that? That's a squared minus b squared. So that when you see a difference of squares, you're like, aha, life is good. I can work with that. I can work with that. You might say, well, what about other things, fancy things? What if I wanted to do, say, long division? We actually won't do that. We may mention it in passing, but that's not our goal. Our goal is to keep it simple. There's so many fun things we could talk about. Okay, maybe let's talk about one more thing that might happen. And, because we still have space, right? We should use up our space. What if we encountered a problem, say something along the lines of x to the fourth minus 3x squared plus 2 equals 0. Could we solve this? And you might say, well, fourth degree, forget about it. Hopeless, hopeless. Well, wait a second. We wouldn't ask you anything unless there was some hope. So what can we do? What can we do? Well, here's sort of something to notice. Say, well, hey, I only see even powers. Okay, well, that's a good sign. So if all I see are even powers, then can I use that? Well, yeah, what we can do is we can think of this as, oh, this is like x squared squared. That's another way to think of x to the fourth minus 3x squared and plus 2 equals 0. And now our great aha, we say, let's give something a name. Recall it. Oftentimes, a lot of algebra comes down to simplifying and changing names. And that's not even just algebra. Calculus, you have this notion of substitution, where you're substituting one name for another name. So for instance, you can say, oh, well, let's let capital Y equal x squared. And now you have capital Y squared minus 3 capital Y plus 2 equals 0. And then off to the races. We can then work with it from there. So that's something that you might see. But again, you have the tools. You can do this. Polynomials, we're ready. We're ready. The next thing for us to talk about are exponentials and logarithms. Now, exponentials show up a lot when it comes to solving differential equations. And that's because the exponential function is so nice. The derivative of the exponential function is the exponential function. And the integral of the exponential function is the exponential function. In other words, it's something where the derivative has a mild effect, if any. And because of that, it becomes a natural candidate for working in many problems. So it's a function we're going to see a lot. So we want to make sure we're comfortable with working with the exponential and its related inverse, the logarithms. Now there's a couple of rules to remember. Namely, if I have e to the a, e to the b, well, that's e to the a plus b. So you add, okay? Not multiply, you add. Well, when can you multiply? Well, e to the a to the b. Well, that's e to the a times b. 1 over e to the a is e to the minus a. And e to the 0 is 1. These are things we should be comfortable with because we're going to be having to do a lot of manipulation. Now, rules for exponentials turn into rules for logarithms. So for instance, the fact that when we multiply, we're adding the exponent tells us, oh, a log of multiplication becomes addition. So in other words, logs are helpful for separating. They can also, of course, do the opposite, which is combine, but we have this nice fact. And log of a to the b is b log of a. So that says that, oh, if you have an exponent, it can come down. But of course, vice versa. If we have a constant, it can come in. And so, rules work both ways. That's the nice thing about an equal. It goes in two directions. If we have a log of 1 over a, that's a minus log a. So a minus means something was downstairs, and a log of 1 is 0. Now, why are these two so closely related? We didn't write that down, but let's go ahead and say it. Namely, that they're inverses of each other. So we have natural log of e to the x is x, and that's the same as e to the log of x. Now, you might say, but let's not and ha at this point. All right, so what's a way we might see this? Well, in the process of solving, we might get some expression. So let's just make one up. And, well, of course, I actually wrote one down, so I just don't want to be completely random. Suppose we see log of y plus 2 minus log of y minus 3 is equal to 3 natural log of t plus some constant c. And our goal is solve for y. Now, of course, the challenge is there's multiple y's, right? Because what do we see? Well, we see 1, 2. Now, when there's only a single y, then that's easy. We have one y to rule them all. But here we don't. So we somehow have to find a way to combine them together. Sometimes it's possible, and those are the times when we ask. Sometimes it's not, and those are the times we don't ask. And but what do we do here? What can we do? Well, we say, hey, we see subtraction. So if you think about the fact that subtracting puts something downstairs, and then, of course, addition becomes multiplication, this really says, oh, we can rewrite this as log of y plus 2 over y minus 3. All right. Now, we want to get rid of the logs because there's y's are inside. And we say, well, is there a way to get rid of the logs? And that's where we use the fact that we have inverse functions. So we're going to say, oh, let's take all of this e to that. Well, of course, if we do it to one side, do it to the other side. Everything should be fair. 3 log t plus c. All right, so what do we have? On the left, well, e and log are inverses. They undo each other. So we're back to y plus 2 over y minus 3 equals, now here, let's do this in a little bit of slow motion. Okay, e 3 log t. Now I'm going to use the fact that there's a plus, say, oh, plus says I can separate. So I'm going to say, okay, so that's e, and this 3 log t, I'm going to move that up. So that's log of t cubed times. I don't know why I'm emphasizing that. Probably because I've cried tears before over students and grading like, why did you make it plus? And so in some sense what you're seeing here, this is my therapy session. When I'm like, well, I really don't want to see this again. I really want people to succeed. All right, so, well, all right, back to our story. Y plus 2 over y minus 3. The e to log t cubed, like we saw before, becomes t cubed. Now, what to do with this e to the c? We can leave it as e to the c, but when we write c here, it's understood that c is representing a constant. So if I take e to a constant, the result is a constant. And so what we can do is say, well, let's just write in another symbol that's a constant. Now, I tend to just reuse the same symbol, but just so that people don't be like, what? How did you do that? I'll use the letter D. So in other words, this part right here is D. And we're going to talk about this again, but the nice thing we'll write down now is that constants are like sponges. And what do we mean by that? Well, it means that we can absorb constants. So if I add two constants together, I have a constant. If I multiply two constants, I have a constant. And so here, e to a constant is a constant. All right. Already, it's looking a lot better. So, what can we do? Well, now we'll get rid of fractions. I'm nervous about fractions. That's because, you know, I've made mistakes before when fractions are involved. And so I said, okay, I'm not going to make that mistake again. Probably I'll make a different mistake, but, you know, not that one. And so what we'll do is we'll clear out our fractions. So we do, you can call it cross multiplying, right? So if you think of this d over dt cubed over 1, you cross multiply, and we end up with y plus 2 is equal to y minus 3 times this d times t cubed. Well, of course, we can expand. So this would be dt cubed y minus 3 times dt cubed. Now you might say, aha, Steve, absorb. Well, but be careful. Here, we have to have this d and this d are the same. So I don't want to just make this an arbitrary e, because that would make it say, oh, these are like completely independent. And they're not. They're not. So constants are sponges, but they're not super sponges. You have to be careful. All right, so now we will rearrange, which is to say, we'll move this term with a y across, this term without a y across. So what we're doing right now is algebra, right? What is the spirit of algebra? Algebra can be reduced down to a simple idea, which is simplification. That's the goal. The goal of algebra is to simplify. And if we simplify enough, what we see at the end has another name called the answer. And so that's our goal, is to keep simplifying until what we have at the end is the answer. All right, so when we subtract the y, I'll go ahead and factor it out because I'm running out of space. We'll get 1 minus d times t cubed times y equals, on this other side, minus 2 minus 3 dt cubed. And finally divide, and lo and behold, what do we end up with? We see that y is going to be equal to minus 2 minus 3 times d times t cubed over 1 minus d times t cubed. And we're done. You know, we probably didn't think, starting with this expression, we'd end up with that expression, but that's okay. We don't have to be creative. We just have to be patient, work it through, and life is good. Life is wonderful. So be ready. Be comfortable working with exponentials and logarithms, and in particular, being able to do some basic manipulation, because we will see this kind of thing again. The next thing we want to talk about is complex numbers. And you might be like, what? I was hoping we're going to be keeping it real this semester, but no. We're going to have to deal at various points with complex numbers. And you might wonder, well, why do we have to? Aren't we modeling like real situations? You know, motion of a spring. Does that have anything to do with complex numbers? And it turns out that oftentimes real models end up with complex solutions in some sense. Now, what are complex numbers? Well, there's a number which we like to call I, and then depending upon what kind of engineer you are, you might call it J, but we're in math. This is a math class, so we're calling it I. And this number has this property that when you square it, it becomes -1. All right, so I squared equals -1. That's the first thing to remember. And the second thing to remember is that there's this cool fact that says e to the I theta is cosine theta plus I sine theta. Now this is why complex numbers sort of inherently show up in the background. Whenever we have anything which involves sines or cosines, for instance, a spring, that behaves like a sine or a cosine. In the background was, oh, actually, it's an exponential function, just happens to have a complex part involved. And we're like, oh, okay, I'm down with that. So how do we do this? And what might we need to do? Well, something we might need to do might be the following. Suppose we have this expression, and 2 minus 3i times e to the 4it, and now the goal is find the real and imaginary parts. In other words, when we think of a number, the complex numbers, there's the real part and the imaginary part. So the imaginary part is I times it. The real part has no I involved at all. So how do we do such a thing? Well, it's nothing too surprising. Say, all right, 2 minus 3i is 2 minus 3i, e to the 4it. So in this case, I can come back to this formula and say, oh, this theta is 4 times t. So I'm going to replace this theta by 4t, and I'm going to replace these thetas by 4t. So this becomes cosine of 4 times t plus I sine of 4 times t. All right, now our gut says FOIL. Let's go with our gut, because our gut is right. Yeah, see how we have like 2 terms here and 2 terms here? And so we FOIL. That's it. Isn't that easy? It's like, what? That's what I thought I should do. And it's what we do. Ah, life is good. Life is wonderful. All right, so we begin. So we have the 2 times the cosine 4t. So that's 2 cosine 4t. So that's real times real. And now I'm going to do imaginary times imaginary. So that was the first, and now I'm going to do the last. So wait a second, that's not FOIL, that's FLIO. Yeah, that's okay, that's all right. Now why that? Well, because when I do just the imaginary parts, I'll have an I squared. I times I becomes -1. So we have I squared, that's -1, times -3. So 2 negatives make it a +3, and sine of 4t. All right, so we have the reals and the imaginaries, and that gives us this piece. And then, like, oh, well, what comes next? Well, now do the outer, and so that's 2 I sine 4t. So, well, I'm going to factor an I out. So that's 2 sine 4t. And our last part, the inner part. Okay, again, there's an I, and then a -3, and a cosine 4t. We have the I, so -3 cosine 4t. And there we go. There's the real part. There's the imaginary part. And life is good. And that's it. And that's the kind of thing that we might be expected to do. Nothing too exotic, very simple, as long as you can remember this nice fact, e to the I theta is cosine theta plus I sine theta, and just think FOIL, expand. Gather the real parts, gather the imaginary parts, remembering, of course, I squared equals -1. Life will be good, nothing complex. All right, good. So let's talk about systems of equations. And this is a really, really important thing. You're going to do this a lot. You might hear me call this bread and butter, because this shows up again and again and again. And so you want to be able to handle this. And so when we talk about systems of equations, we're talking things like 2 equations, 2 unknowns, or maybe 3 equations and 3 unknowns, or maybe 17 equations and 17 unknowns. But in that last case, there's usually a shortcut. So don't get too nervous when I say that. So what do we have? Well, we have a bunch of equations, a bunch of unknowns, and that sounds complicated. And we think about, well, what is algebra about, right? Algebra is simplifying. So you say, you know, what's easier than 2 equations, 2 unknowns? 1 equation, 1 unknown. So our whole game plan, and it's a very simple one, eliminate a variable. If we can eliminate a variable, then what we'll have is something easier to work with. And we like easy. It's one of our favorite things. So we say, okay, how do we go about eliminating a variable? Well, there's 2 main strategies. One is substitution, and that says you solve for one variable in terms of everything else, and then you take that expression and plug it in. That works. But the second strategy, cancellation, and I really want you to practice that one. This is a really nice way to approach. What do we do? Well, we say, hey, let's knock out a variable. And we do it by combining things in such a way that we get cancellation. So most of the time when we talk about systems of equations, and essentially like 95% plus in our class, we're talking about linear systems of equations. So the way you do cancellation is you multiply or scale one equation by a constant, add it to another, so that things cancel out. All right, let's look at an example. So suppose we have the following. 3x plus y is equal to 5, and 5x minus 4y is equal to 14. All right, 2 equations, right? We can count 1, 2. 2 unknowns, x, y, And you say, all right, good. This is what we want to be talking about. So where do we go from here? Well, we want to cancel either the x's or the y's. Now, there's not an automatic do this, do that. My suggestion is to say, look for things which are simple. And oftentimes you say, well, there's one that is really close, and that's easier to work with. In our case, I see that the y here, that's a 1y. Coefficient of 1 is really good to work with. So let's use that. So we're going to scale this equation by some number, combine it with that equation, and produce a new equation. All right, well, what's the right number? I want something to multiply by y so that when I add negative 4y, I get 0. So I say, aha, multiply by 4. So you get 3 times 4 is 12 plus 5 makes 17x. 4y, subtract 4y, makes 0y, which is intentional. That was our whole goal. 5 times 4 makes 20. Add 34 makes 34. And notice we're down to one equation, one unknown. This is our favorite kind. 17x equals 34, so that tells us, aha, x equals 2. Nice. And now we can take that and plug it in. We can actually plug it into either one. It doesn't matter. Well, let's plug it into the top one. 3 times 2 makes 6, plus y has to equal 5. So what's the number that when you add it to 6 makes 5? The answer, -1. All right. So there we go. X should be 2. Y should be -1. Life is good. And we're done. So you should be able to do this automatically. And don't worry, you're going to get a lot of practice. A lot of practice. And so that by the end of your time in the math classes, when you go to your classes down the road, you're just going to be like, yeah, 2 equations, 2 unknowns. No problem, no problem. All right, well, I can't help but notice we have an awful lot of space left. So let's try 3 equations, 3 unknowns. And most of the time, if we do ask for that, it'll be not too bad. I don't know if this one's going to be not too bad. I always get nervous when I haven't worked it out, but let's find out. So I have a problem I wrote down. Suppose we take A plus 2B, and of course, you know, one of my favorite things is whenever I say 2B, is it not 2B? No, I think it's 2B. We'll find out. Minus 3C equals 11. 2A plus 3B plus 4C should equal 9. Minus 4A plus 5B plus C should equal 6. All right, there we go. Okay, so, but our mantra remains the same. Simplify, simplify, simplify. And the way we simplify is we look for good numbers to cancel. Now, here, I'm going to use this A, because it has a nice coefficient to work with. All right, so what do I mean by I'm going to use it? Well, I'm going to multiply the first equation by a constant and add to the second equation so that I get cancellation of the A's. So I say, well, I'm going to represent that with an arrow. Say, look, I'm using the first equation to combine it with the second equation, but not just directly. I'm going to first multiply by -2. Now, similar, I'm going to say, well, look, I want to cancel with the third equation. All right, so again, I'm going to use the first equation to combine it with the third equation. What's the right thing to multiply by here? Well, now it's a +4. All right, so what happens to that first equation? Answer, it just stays. So we have A plus 2B minus 3C equals 11. Now, careful. We're going to multiply by -2 and add. So everything gets multiplied by -2 when we add. Negative 2a plus 2a, no more a. Negative 2 times 2b is minus 4b plus 3b makes a minus b. Minus 2 times minus 3c means positive 6c plus 4c, that's 10c. 11 times negative 2 makes minus 22. Minus 22 plus 9 would make that minus 13. Okay, so minus b plus 10c equals minus 13. All right, now, next one, 4. So 4a minus 4a, 0a. 8b, because that's 4 times 2b is 8b, plus 5b, that makes 13 times b. Minus 3 times 4 is minus 12c, plus a c makes minus 11c, and then 4 times 11 is 44, plus 6 makes 50. All right, so 13b minus 11c is equal to 50. Now, let's pause and see that, what's happened? We started with 3 equations, 3 unknowns, and now we have this sort of smaller problem, 2 equations, 2 unknowns. Woohoo! Nice! This is great. This is wonderful. And it means we're on the right track. Okay, cool. And well, let's see what happens next. Well, let's keep working it. And what can we do? Well, we have this minus b, and we can multiply. Well, yeah, it is what it is, minus 13. All right, because, oh, sorry, just positive 13, right? So minus 13b and 13b. All right, got to be careful here. You don't want to make too many mistakes. That's one of the things about algebra. You have to be really careful, and it's easy to make a small error. Okay, first equation, second equation, and we're just changing the third equation. Okay, so minus 13 plus 13, 0. 130 subtract 11. All right, so 130 subtract 11 is 119? Yes? No? Yes, it is. All right, so 119c. Ooh. All right. Now, 13 times 13 times 13. Well, that's a square. We have those memorized. That's 169. Well, or you can just work it out. That's minus 169 plus 50. Minus 169 plus 50 is minus 119. And these numbers look terrible, except they're the same, which tells us what? Well, it tells us that, lo and behold, c is negative 1. Now, this is great. So we worked out, now that we have that one, we're just going to work our way back up. So now we have minus b, and since c is negative 1, that's minus 10 is equal to minus 13. We can add 10, so that says that negative b is negative 3, or b equals 3. So we have c, now we have b, and so now we can work it back up. So we have that a plus 2 times b, so 2 times 3 makes 6, minus 3 times minus 1, that's a plus 3 equals 11, or a plus 9 equals 11. So that says that a is 2. And so our answer, a equals 2, b equals 3, c equals negative 1. Done. And that's it. Now, if these numbers make you nervous, I just want to tell you right now, don't panic. The numbers that you'll see are going to be much simpler to work with. And you'll have other ways to to solve these. Oftentimes, you'll get numbers that you'll see that, aha, there's better ways to approach this. Don't always get stuck in the mechanical, I have an algorithm, I'm just going to go in blindly. You're smart. I know you're smart because you're taking this class. Use your smartness. And by that I mean, look at what you have and say, what are things I can do to make it easier for me? Because that's our goal. Let's make life easier. All right, well, we still have a few more things to talk about. In the middle part of the course, we're going to be talking a lot about matrices. And so we want to be able to use them. Now, we're going to spend time doing a review of matrices when we get to that point, but I just want to give you a heads up that it's coming so that you're not like, what? Matrices? I had no idea. And it turns out that these are really useful. Now, sometimes this is called linear algebra. Notice that we have the word algebra attached. So there's a lot of algebra involved. And the good news is that we're going to really hyper-focus on just 2 by 2. Now, that's a big simplification, and a lot of the ideas do generalize, but of course, as you get larger, things get more subtle, and but that's another story for another class. A couple things you want to probably be able to do. There's something called the determinant, and so we represent that with a bars. Now this looks like an absolute value. It doesn't have to be a positive number, though. It could be negative. And it's essentially taking the matrix and associating it with a particular number, which has some sort of geometrical interpretation. We won't worry about that right now. And how does it work? Well, you go down the diagonal, a times d, and then you go on the other diagonal, but you subtract. So AD subtract BC. Not too bad. There's something called an inverse. Now, there's another idea called multiplication, which we didn't write down, but we'll skip that for now. And how does an inverse work? Well, the idea of an inverse says that when you multiply two things, you should get 1, or whatever 1 corresponds to. So in general, we say, hey, if I have a 2 by 2 matrix, the inverse looks like 1 over this number AD minus BC. Like, what? Wait a second. That looks really similar. Yes, it is. It's the determinant. And then you swap the diagonal entries and then put signs on the anti-diagonals. Again, we'll see this later on. Now, one more thing that we will see that you maybe haven't seen before, just saw in passing, but I want to let you be aware of it because we will use it at one particular point in a variation, which is called Cramer's rule. Now, Cramer's rule is a way of saying, hey, if I have a system of equations, maybe 2 equations, 2 unknown, could be 3 equations, 3 unknowns, 4 equations, 4 unknowns, but let's leave it to 2 equations, 2 unknowns. Then what I can do is I can transform that and rewrite it in the language of matrices. In some sense, you could argue that what matrices are about is a way of writing systems of equations in convenient ways, and in particular in ways that allow us to use tools. So the study of matrices is the study of systems of equations, and that can be readily justified. So that's not just like, oh, no. That is what it is about. Now, in this way, what happens? Well, we can solve for x and y. Now, there's actually 2 ways we can do it. One is to take the inverse and then just multiply PQ times the inverse, but we're not going to do that. Instead, we're going to have, there's this fun fact, which says that x is the ratio of 2 things. Namely, you have AD, BC, like, oh yeah, like that, right? Yeah, exactly like that. Then upstairs, what you have is a determinant, another determinant, where what you do is you think of, well, the first column is the x column, the second column is the y column, right? Because you see that the AC is attached to the x, the BD is attached to the y. So these are the coefficients. So, okay, if I'm solving for x, replace the x by these numbers, PQ. If I'm solving for y, replace the BD by PQ, and take that determinant. All right, so let's do just 2 quick examples. Like I said, we're going to go through this much more thoroughly when we get to this point in the course, but it's good to do an example, right? Okay, so suppose we ask the following. Solve for lambda so that when we take the determinant 3 minus lambda, 2 minus 5, 1 minus lambda, we get 0. This is a particular thing that you're going to be doing a lot. And so you want to be comfortable with this type of procedure. And well, what do we do? Well, it's determinant, right? So take the diagonals, subtract the diagonals. So that's the same as saying, oh, 3 minus lambda times 1 minus lambda, subtract negative 5 times 2 equals 0. Now we expand. Lambda times lambda makes lambda squared. We have minus 3 lambda minus 4 lambda. That's minus 3 lambda minus lambda. I've got minus 4 lambda. I was getting ahead of myself. Yeah, that's a very dangerous place to be. And we have 3 plus 10 makes 13. And that equals 0. All right, so now we just need to solve this. Now we can try to factor. 13 is really hard to work with. It's a prime number. So not a lot of ways to break it apart. There's only one way, which is 1 and 13, and that's just never going to work with that 4. So we can use quadratic formula. We can also actually use completing the square. So how would completing the square work? Well, we'd have lambda squared minus 4 lambda. You say, well, what do I need to add? Well, I need to add 4, right? Take the middle term, divide by 2, square it, plus 4. But you say, well, look, I don't have 4, I have 13. Okay, so add 9, because 4 plus 9 equals 13. So this says lambda minus 2 squared, and then I'll move the 9 across, is negative 9. All right, now we can apply square roots. Say, all right, well, we have lambda minus 2. Square roots are plus minus. Square root of 9 is 3. Then I need to say, I need some number that when I square it gives me negative 1. We have a number called I, right? Because that was the property of I. I squared equals negative 1. Finally, add 2. And so we end up with 2 plus minus 3i. So here, turned out that we needed a complex number. So even though these were all real numbers that were sort of somehow lurking in this matrix, we ended up with complex. What does that mean? We'll get there. We'll get there. All right. Well, again, we have space. So let's try one more. And in fact, a little bit of deja vu, a callback, if you will. So suppose we have 3x plus y equals 5, and 5x minus 4y equals 14. So remember, we talked about this with 2 equations, 2 unknowns. So we already know the answer, and so let's just solve for one of the variables. Let's solve for x. And so I'm going to use Cramer's rule. So what does Cramer's rule say? Well, the downstairs is a determinant where it's the coefficients. So it's 3, 5, 1, negative 4. The upstairs, since we're solving for x, we're going to replace the x coefficients by the terms on the right, 5 and 14. The y coefficients remain the same. So what do we get? Well, we have 5 subtract 4 is minus 20. And then we're going to subtract 14 times 1, so that's minus 14. We get 3 minus 4, that's minus 12. Subtract 5 times 1 is minus 5. So what do we have? Minus 34 over minus 17 gives us 2. And we're done. And in a similar way, you can solve for y. All right, so anyways, 2 by 2 matrices, they're coming. Be ready for them, and it's going to be great. And I'll tell you right now, my experience has been that this is a part where students are like, oh, this is going to be terrible. And then they get there like, yeah, this is not so bad. And you're going to do pretty well on it. You know, you have to practice and you have to be able to handle a few things, but don't worry about the matrices. You should be like, matrices, woohoo! Steve said this was good, because it is. It's good. I endorse it. As we get close to the end of the class, we're going to have one more beautiful thing show up. Partial fractions. And if you thought, partial fractions, I thought I was done with that in Calc 2. You know, that was just the beginning. We're going to have like a whole 2 weeks where it's like, this problem gets partial fractions, that problem gets partial fractions, every problem gets some partial fractions, woohoo! Because it's going to be used a lot. So we want to make sure we're comfortable with it. Now, we will do a more thorough review later on, so this is just more of a, it's coming, be ready. So let's just remind ourselves what partial fractions are about. So the idea is you have a function that looks like polynomial upstairs, polynomial downstairs. Now the problem is we really want to break things into small pieces, because small pieces equals something we can do. Large pieces equals ugh. So that's what the algebra part is. We're simplifying by breaking it into smaller, what you might call bite-sized pieces. So how do we go about doing that? Now, if you think back to when you first learned about partial fractions, there was a process. It started with doing long division. Now, I'm going to go ahead and tell you, good news, we don't need to worry about long division. You're not going to have to do it. And so all the problems that we do, no long division is involved. So where do we start? Well, factor the denominator, if they haven't already done that for you. Then you're going to say, okay, I want to pull it apart. And so you're going to use your denominator to say, what do my pieces look like? So if you think about how you add things, you say, well, I get a common denominator by sort of multiplying out, you know, what my pieces in the denominator are. So when you pull it apart, you say, well, for every piece that's downstairs, I'm going to have a term. And so that's how you find the form. There's a few subtleties that come into play. Things like, do you have a linear versus quadratic? Things, do you have repeated terms? And handling that, we'll get into those details later on. But once you have the right form, you're going to say, well, I know it looks like this up to some unknown values. So there's like an A, B, C, D, however many terms you have. And so I need to solve for A, B, C, D, however many terms you have, which gets us back into finding that. So how do you solve for the unknowns? Well, there's lots of ways to do it. The basic mantra I follow is clear denominators. I like to avoid fractions. I just, you know, I think I probably had a bad fraction many years ago, and ever since then I've been like, okay, no more fractions for me. And so I clear my denominator, get rid of fractions, and then I say, all right, make good choices. Because I have two things which are equal to each other, and they always have to be equal to each other. Well, if they're always equal to each other, then that says I can just pick values and say, okay, what if I pick a value of 0 or 5 or 7? Now, that's just choices. What makes a good choice? Well, make choices where things vanish. And the more things that become 0, the better life is. And so that's how you go about making good choices. There's other things you can do. You can group coefficients together and just say, hey, I really have polynomial equals polynomial, so coefficients have to match with coefficients. And again, we'll go through all of these things later on. But for now, just to sort of whet our appetite just a little bit, let's do one problem. Okay, so suppose we do partial fractions to the following: 3s squared minus 7 times s plus 15. And we'll divide that by s minus 2 times s squared plus 9. All right. Now, remember, we said don't worry about long division because that's not our jam. That's maybe in Calc 2 you'd have to do that. But here, we're the nice class. We're the friendly class. And we say, okay, all right, so we have our expression, polynomial over polynomial. Our denominator's been factored. Good job. So there's really just two steps, right? We have to find the form. So we say, well, there's a piece that looks like s minus 2. There's a piece that looks like s squared plus 9. So this has to look like something over s minus 2, and then something over s squared plus 9. Now, what are the somethings? Well, on the top, say, well, I don't know what goes here, so that's a. Now, here's one of those subtleties I mentioned. Notice that this is what we would call irreducible quadratic. In other words, we can't factor it without getting complex numbers. And so what we do is we say, that's fine, we'll leave it as quadratic. The side effect is we have to just add a little bit extra upstairs, b times s plus c. Now, spoiler alert, how many unknowns do we have? We have 3. The number of unknowns that you have has to match the degree downstairs. So what's the degree downstairs? Well, s times s squared, that would be s cubed, 3. So 3 equals 3. So good sign. All right. So now we say, okay, so these two terms have to be equal. So the only thing is, what are a, b, and c? So we're going to say, all right, everything we're going to multiply by s minus 2 times s squared plus 9. Both sides. So we get rid of our fractions. So on the left hand, we get 3s squared subtract 7s plus 15. On the right, in the first term, the s minus 2's cancel, so we get a times s squared plus 9. In the second term, the s squared plus 9's cancel, so we're going to end up with b times s plus c times s minus 2. All right, so what are we down to? We have 3 unknowns, the a, b, c, and s can be arbitrary. So, as I said, you can start expanding or make good choices. So I would say make good choices, and only when you've run out of good choices, then do you start expanding. Okay, so what are some good choices for us to be making here? Well, see how we have this s minus 2? Can we choose a value for s that makes that just go away? We can. All right, so let's choose s equals 2. When we do that, well, we'll have 3 times 4, which is 12, subtract 14, add 15. Here, 2 squared plus 9 makes 13a, and then that whole term goes away. We say, okay, well, what is this? 15 subtract 14 is 1 plus 12 makes 13. So 13 equals 13a, or we get a equals 1. We've already solved for one of our unknowns. And it feels like we just started, because we just started. See how a good choice is good? It helps you to simplify. All right, well, let's try something else. Now, is there anything else that knocks out a variable? 0. See how that b is multiplied by s? Now, by the way, a good rule of thumb is whenever a math teacher asks a question, the answer is usually 0, 1, or look for something written on the board. So 0 is a good one to go with. And 0 cancels out lots of things. So 0 is friend. 0 is friend. Okay, so s equals 0. All right, 0, 0, 15. All right, we have 0 plus 9 is 9, 9a. But wait, we know a, so 15 equals 9. And then here we get 0 plus c, so that's c, and 0 minus 2 is minus 2. So 9 minus 2c. Or, what does that say? 15 subtract 9 would be 6. So minus 2c equals 6, or c equals negative 3. All right, so now we found a and we found c. Is there any other choice that makes things disappear? No. So what do we have to do? Well, we can now say, look, but we only have one more thing, one last one to solve. So let's just pick anything. So since I can pick anything, I can pick 1. So s equals 1. Well, that's 3 minus 7 plus 15. You know, that's the nice thing about plugging in 1. It's easy to plug in 1. 1 plus 9 is 10, 10a. Wait, we know a is 1. So that's 10. Plus, and then here, we know c is negative 3. And so we have b minus 3. Yes, right? b times 1 minus 3. And then we have 1 minus 2 is minus 1. Okay, well, let's clean this up. 18 minus 7 makes 11. That equals 10. And then, well, if we distribute the minus through, be careful here, we get plus 3 minus b. All right, so, well, that says the same as 11 equals 13, subtract b. So what is b? B has to be 2. So the punchline here is that our original polynomial over polynomial you can pull apart as a, which is 1 over s minus 2, plus, then we have b times s plus c. So b times s makes 2s plus c minus 3 over s squared plus 9. And that would be the partial fraction. So that's just another way to write that expression. And that's the idea. That's the kind of thing that you'll have to do. Some will be about this level of difficulty, some will be easier, a few will be harder, but with practice, none of them will be impossible, and they're all going to be doable, because after all, we want you to do them, right? Of course. Well, that brings us to the end of our algebra review. And so if you were able to say, hey, I know all these things, you're in great shape. And if you're like, a little bit iffy on some of these things, don't worry. Don't worry. There's lots of practice coming. And for things like the matrices and the partial fractions, we will go into those in more depth when we hit that topic in the course. A couple of more tips, pieces of advice. Some of these are algebra related. Some of these are just more general, but things that are helpful. One piece of advice, write legibly. There are many cases where students are not able to read their own handwriting. And there are examples where you might have a problem which involve things like the letter S versus the number 5. And if you're not able to distinguish, is that an S or a 5? You're in trouble. Because I have seen this happen before, where people confuse the two, and then they're in work. And then they're in trouble, not they're in work. Wow. All right. Well, okay. I'm looking ahead, because I wanted to say the next thing is check your work. You know, take your time. I know when you feel like you have an exam or a quiz, it's like, this is a speed test. But we don't want you to run so fast that you make errors, because errors tend to snowball. So there was a time when I graded a problem which involved partial fractions, and in particular it had the following. It was s squared plus 2s plus 5. See, if you confused this 5 as an s, you're in trouble. And a large number of students wrote this as s plus 1 squared plus 2 squared. And a large number of students wrote this as s plus 2 squared plus 1 squared. And then I thought to myself, wait, they can't both be right because they're not right. So what's the right answer? Can you tell? And is it like, well, the world will never know which one is right? No, actually, we can tell which one is right. We can say, well, imagine we expand it, right? Because we know how to take s plus 1 squared. That's s squared plus 2s plus 1. We know how to take s plus 2 squared. That's s squared plus 4s plus 4. So this is right. And just a small, quick, whenever you factor, just multiply it back out to make sure things match. The small things will help prevent big things from going wrong. So be careful. And while you're being careful, also, please don't be creative. And I know it's a test, and you're like, this is, I'm going to make sure I get things right, and I'm stuck. Well, let me start coming up with new ideas. Now, what are examples of being creative? Well, you might say, well, I have this expression, 1 over, I don't know, let's say x squared minus 3x plus 2. Like, what can I do? Well, idea. I'll think of this as 1 over x squared minus 1 over 3x and plus 1 over 2. And does that work? No, it doesn't. And as soon as you've been creative, everything from that point on, hopeless. Forget it. So just follow the rules. And in some sense, you might say, well, what can you do? We have something. We're not going to give you something where you don't have the tools. So think about the tools. The tool in this case is partial fraction. This reminds me, of course, of something, which is to say that when I look at plus signs, plus downstairs is a very sad thing, because that means, well, maybe I shouldn't say sad, but it means there's more work. But a plus upstairs, that's actually something where we're happy, because that plus sign is used to pull things apart or to pull things together. When it's downstairs, it doesn't work the same way. So be careful, know your rules, and maybe one more piece of advice, which won't be a surprise, is to say that your parentheses, however you spell that word, parentheses are friends. Use them. So a lot of times people make silly mistakes where they forget to put parentheses and they forget to distribute through. And for example, minus signs. A lot of times minus signs get lost. So keep track, use parentheses to help make sure that you don't lose any points. Because our goal is to get all the points, to learn everything, to do well. All right, this was a very long review, and thank you for being so patient. By practicing your basics, you'll do well. You'll succeed. I believe in you. All right, see you later.